Module 9, Lecture A, Print and Input. By the end of this lecture, you will be able to use print with custom separators, end characters, and file targets to control console output formatting. Use input to read user input safely and convert it to appropriate types using other built-ins. And structure code so that print and input usage can be redirected or mocked for testing. Controlling print output, custom separators, and endings. Console output may look like a simple stream of lines, but you often need more control over how values are combined and how each line ends. A separator controls how multiple values are joined in one output, and the ending controls what appears at the end of that output. By default, values are separated by a space, and the line ends with a new line, but these are only the starting settings. Adjusting the separator and ending lets you format output for different purposes, such as status messages, data reports, or interactive prompts. When printing multiple values, choosing custom separators helps group information clearly. Instead of always using spaces, you might use slashes for dates, commas or arrows for product codes, tabs to align data for spreadsheets, or semicolons for certain import tools. In terminal interfaces, decorative symbols can also make menus or progress indicators easier to read. The key idea is to pick separators that show structure and meaning rather than relying on the default. Custom endings let you control how each line of output finishes, which is especially useful when you want everything to stay on the same line, such as for a progress indicator or loading animation. By replacing the usual new line with an empty string or another character, you can make the output flow continuously without moving to a new line. This is also helpful in interactive programs where you want the cursor to remain on the same line as the prompt. In addition, custom endings can add extra spacing or markers between sections or records, improving the clarity and readability of console output. Python code, custom separators, and endings. This section focuses on simple console output formatting. You will see how to use print separators to join multiple values in a clear way, and how to use print endings to control exactly where lines break. Finally, you will combine separators and endings to produce clean, readable output for basic console programs. This line shows the default behavior of the print function in Python. When you pass multiple values to it, they are automatically separated by a single space. After printing these values, the function ends the output with a new line. This makes it easy to display text in a simple, readable way without adding any extra formatting. This line of code prints a date using a custom separator. Instead of the usual spaces between the values, it inserts slashes between the month, day, and year. As a result, the output appears in a standard date style, similar to how we typically write dates like April 15th, 2025. The key idea is that you can control the characters used to separate the date components. This line of code prints the words start, middle, and finish, but instead of separating them with spaces, it uses arrows between each word. This changes the default spacing so the output looks like a path. As a result, the sequence from start to finish is easier to see and understand as a clear progression. This line of code prints a short shopping list with the items eggs, milk, and bread. It uses a custom separator made of a comma and a space to clearly divide each item. This formatting makes the output easier to read and resemble a typical written list. This line prints the word loading and changes the usual line ending, so it shows 3 dots instead of moving to a new line. As a result, the next output appears on the same line. This creates a smooth, continuous display that works well for showing ongoing processes or updates. The code prints the word done and changes the usual line ending so that it uses an exclamation mark before moving to a new line. This replaces the default new line character with a custom ending. As a result, the word done appears directly after the previous output, such as loading, creating a smooth transition that shows loading followed by done with an exclamation point on the same line in the console. This line prints the message section 1 complete to the console and then adds 2 new line characters, creating an extra blank line. Using this custom ending helps visually separate different sections of output. As a result, the console becomes easier to read and organize, especially when displaying multiple sections of information. This line of output shows the word temperature, then the number 72, then the word Fahrenheit, using a colon and a space to separate the label from the value. This creates a clear label and value format. The line ends with a period and then moves to a new line so that any following output starts cleanly on the next line. This script shows how to customize the behavior of the print function by changing how values are separated and how each line ends. It first illustrates the default behavior where values are separated by spaces and each call ends with a new line. Then it demonstrates using different separators, such as slashes for dates, arrows for paths, and commas for a list to make the output more readable. The script also changes the line ending to control whether output continues on the same line, for example by adding dots to suggest a loading process. Finally, it combines custom separators and endings to format a temperature reading, showing how these options work together for precise console output formatting. Redirecting print output. When we talk about printing in a program, it is not limited to showing text in the console. Printing really means formatting text and sending it to some destination that knows how to handle characters. This destination could be the console, a file, a log, or even a network connection. By changing only the destination, you can keep the same print calls in your code, but redirect the output wherever you need. This makes your programs more flexible and easier to adapt to different environments without rewriting the output logic. Redirecting output is useful when you want to capture data for later analysis or for users who are not watching the program in real time. During development, you may prefer to see progress messages and errors directly in the console for quick feedback. In production, however, it is often better to send these messages to a log file so they can be archived and shared. This is especially helpful in scientific simulations, where intermediate results need to be stored for further analysis. By redirecting output, you keep the simplicity of using print while gaining reliable, permanent logging. Planning for output redirection helps your programs fit smoothly into larger workflows where one program's output becomes another's input. If you design your printed output so it can be easily redirected, you can send it to files, pipelines, or monitoring tools without changing your core logic. Treating output destinations as interchangeable makes your code more reusable, easier to test, and more adaptable. In practice, deciding where your output goes is just as important as deciding what you print. Python code, redirecting print output. This section explains how to redirect printed output so it goes into a text file instead of appearing on the screen. It compares normal printing to the display with printing that is redirected into a file, highlighting the difference in where the output ends up. You learn that by providing a file as an argument to the print operation, you change the destination of the output from the screen to that file. The focus is on understanding how this file argument controls where printed information is sent. The first line stores a message describing that the engine temperature has reached 200 degrees Fahrenheit, so it can be used later for logging or display. The second line stores another message that warns the oil pressure has dropped below a safe operating level. Both lines simply save these warning messages so the program can respond to or record these conditions when needed. The program begins by stating that it will print directly to the console, setting the context for what follows. It then displays a first message about the engine temperature reaching a certain level. Next, it prints a second message warning that the oil pressure has dropped below a safe limit. Together, these lines show how status and warning messages normally appear on the screen, creating a reference point for later comparisons with redirected output. We begin by opening a file called EngineLog in write mode with UTF-8 encoding, so it is ready to receive text. Instead of printing messages to the console, redirect the first message into this file by using it as the output destination. We then send a second message to the same file in the same way. As a result, both messages are saved in the file for later use rather than appearing on the screen. Closing the file after writing is essential because it makes sure all data is actually saved and not left in a temporary state. It also frees the system resources that were being used for that file. In addition, closing the file helps prevent data corruption and lets other programs or processes access it safely if needed. The code reads back messages that were previously saved in a log file. It opens a file named EngineLog in read mode with UTF-8 encoding, using a context manager so the file is closed automatically afterward. Inside this block, it reads the entire file content, trims any extra spaces at the beginning or end, and stores the clean text in a variable for later use or display. The code first prints a message to the console to explain that the file it is about to show contains the redirected log lines. It then prints the contents of that file, which were previously stored in a variable. This displays the messages that were redirected from the console into the file earlier, allowing the user to see and verify the redirected output. This script shows how to redirect printed output from the console into a file for logging. It first prints 2 warning messages to the console, then opens a text file called EngineLog in write mode and sends 2 different messages into that file instead of to the screen. After closing the file, it opens the same file in read mode, reads its contents, and prints them back to the console. The main idea is that you can direct print statements to a file by specifying the file as the destination, which helps record information without cluttering the console. Flushing output buffers. When a program prints text, it usually goes into a buffer first, instead of appearing on the screen immediately. This buffering improves efficiency by reducing how often the system has to write output. However, it can also delay when messages actually become visible. Flushing the output buffer forces all stored text to be sent right away, ensuring that messages are displayed or recorded immediately, instead of waiting for the buffer to fill or the program to end. In interactive or time-sensitive programs, it is important to flush output so users see messages as soon as they appear. Without flushing, a quiz question might not show up before the program waits for an answer, leaving the screen blank and confusing the user. In the same way, a data processing script might seem stuck if progress updates are not flushed. By flushing output after prompts and status messages, you make sure users receive timely feedback and understand what the program is doing. Flushing output is important when a program sends its output to files, logs, or other processes instead of directly to the screen. In systems like automated trading or scientific experiments, if diagnostic messages or sensor data stay in a buffer too long, critical information can be delayed. By forcing the output to be written at key moments, such as after a log entry or a measurement, you reduce latency and make the program's behavior more predictable. This helps ensure that real-time feedback is not compromised by buffering delays. Python code. Flushing output buffers. This section shows how to use the flush option in print statements to control when output is actually displayed. By comparing a buffered countdown where messages appear all at once with a flushed countdown where each message appears immediately, you can see the difference in behavior. Understanding this is especially useful when writing interactive or time-sensitive console programs that need prompt feedback to the user. The script starts by importing the time module, which provides functions for working with time. In this program, it is used to pause the program briefly. These short pauses create a countdown effect by delaying execution between steps. The code starts by printing a message that a buffered countdown is beginning and that the countdown messages may appear together. It then runs a loop that counts down from 3 to 1, printing the current number for each step. After each printed number, it pauses for half a second using the time module's sleep function. This creates a delay between countdown ticks, but because the output is buffered, the messages might not show up on the screen immediately. We begin by printing a message to signal the start of a flushed countdown, letting the user know that output will appear immediately. Then we run a loop that counts down from 3 to 1, printing a message for each step. The important detail is that we enable immediate flushing of the output, so each printed message is sent straight to the console instead of being buffered. This makes the countdown appear in real time, which is useful for interactive programs. Between each step, we pause for half a second using the time module to create a clear delay between messages. This script shows the difference between buffered and flushed output in Python using a simple countdown example. In the first countdown, Standard print statements may cause all the messages to appear together because the output is buffered. After a short pause, the script repeats the countdown but turns on immediate flushing so each message appears as soon as it is printed. This demonstrates how flushing is useful when you need real-time feedback in interactive or time-sensitive programs. Reading input safely. Designing prompt messages. When a program pauses for user input, the message it shows should clearly state what information is needed, in what format, and why it matters. Being specific, such as asking for age in whole years, helps reduce mistakes and confusion. The tone and vocabulary should match the audience, whether they are students or technicians, so they feel supported rather than tested. Clear, concise prompts guide users to enter accurate data without needing extra instructions. To make user prompts clear and reduce errors, you should state all constraints and expectations directly. For example, if a booking system only allows office hour appointments, clearly say that times must be between 9 in the morning and 5 in the afternoon. And if a survey needs a yes or no answer, explicitly list those options. This kind of specificity is especially important in areas like healthcare and finance, where data quality and safety are critical. By clearly defining the required input format, you improve accuracy and make it easier to convert responses into structured data. Effective program messages should anticipate where users might be confused and give just enough guidance to help them respond correctly. Brief examples or short explanations of why information is needed, especially for sensitive data, build trust and reduce hesitation. For complex tasks, it helps to break the interaction into simple, focused questions so users are not overwhelmed. Thoughtful message design turns confusing, error-prone exchanges into simple, reliable data entry. Input-return basics. In Python, whenever you read keyboard input using the input function, the result is always text, no matter what the user types. Even if the user enters something that looks like a number or a date, the program still receives it as a string of characters, not as a numeric value. This means that typing something like 180 gives you text, not a number. It is important to understand this so you can decide how to interpret and convert that text before using it in calculations or program decisions. The input function pauses your program and waits until the user responds, which means the program is temporarily on hold. This blocking behavior is essential for interactive applications, such as quizzes or budgeting tools, where the program must wait for user input before continuing. Understanding this helps you control the order in which things happen in your program and avoid placing input requests in parts of the code that need to run quickly or without interruption. When you use an input function, it returns exactly what the user types, including spaces and punctuation. Because of this, you need to clean and standardize the text, such as trimming extra spaces and making capitalization consistent. If you do not do this, small differences like extra spaces or different letter cases in a word like yes can cause your program to misread the response. By treating user input as raw text and applying simple cleanup steps, you make your program more reliable and easier to use. Python code, input-return basics. Show that when you read user input, it always comes in as text, not as a numeric value. even if the user types a number. Emphasize that the raw input keeps all spaces and capitalization exactly as the user entered them. Then, demonstrate how to print both the data type and a cleaned or converted version of the input, so learners can see how to safely handle and process these values. The program starts by explaining that it will demonstrate how user input is returned as text. It asks the user to type the number 180, including any spaces, and press Enter. The input is then captured and stored in a variable as raw text. This shows that whatever the user types is stored exactly as entered, as a string, even if it looks like a number. The code first announces that it will show the raw text value of the number and its data type. It then displays exactly what the user typed, using a function that reveals the full string representation, along with confirming that its type is a string. After that, it removes any spaces at the beginning or end of the input and saves this cleaned version in a new variable. This trimmed text is then ready for further processing, such as converting it to a numeric value. We begin by removing any extra spaces at the start or end of the text input to clean it up and make it consistent for later processing. After this cleaning step, we show the updated text to confirm that the spaces are gone, but the data is still treated as a string. Then we ask the user to type the word yes, allowing any capitalization or surrounding spaces, to illustrate that user input can appear in different formats. The input function captures this response so we can handle the user's confirmation in a flexible way. The code first displays a message that it will show the raw input text exactly as it was typed, including spaces and capitalization, using a representation-style display. It then shows what the user entered in this detailed form. After that, the program normalizes the input by removing any spaces at the beginning or end and converting all letters to lowercase. This normalization step is important because it makes later comparisons with the input safe, consistent, and easier to handle. The code takes the user's answer, removes extra spaces, and converts it to lowercase, so the text is in a consistent format for safe and reliable comparisons. It then prints this normalized answer to show how it will look when used in later decision-making. The program ends by signaling that the demonstration is complete and noting that it paused at each input step to let the user interact with it gradually. This script shows that the input function in Python always returns text, even when the user types something that looks like a number. First, it asks for a number with spaces, displays the raw input to show it is a text string, then removes the spaces to clean it up, but it is still text. Next, it asks the user to type the word yes with extra spaces or different capitalization, again, showing the raw input, and then a cleaned version where spaces are stripped and letters are converted to lowercase. This process of normalizing input is important so the program can compare user responses consistently. The script also illustrates that the program pauses and waits at each input step until the user types something and presses Enter. Input conversion patterns. When handling user input, first read it as plain text, then convert it into the data types your program needs. Keep these two steps separate and use functions to transform the text into integers, floats, or Boolean values. This separation makes it easier to locate and fix errors because you can see whether the problem occurs while reading the input or while converting it. It also supports clearer validation and transformation before you rely on the data for further processing. When turning user input into structured data, it helps to chain several small transformations. For example, you might trim extra spaces, split a date into day, month, and year, then build a date object, or split a list of course codes by commas and clean and standardize each one. This pattern of splitting, trimming, and normalizing lets you accept flexible input while still producing clean, consistent data. By thinking of the process as a pipeline of simple conversions, you can support many input styles without making your code complex. When handling user input, design your program to keep asking for information until it receives something valid. For instance, a fitness app might repeatedly request a weight until it gets a positive number, or accept a special word to skip the question. In surveys, you can also normalize what users type so it matches the allowed categories and briefly explain the options if needed. Treating input as a conversation like this reduces errors and makes your program more robust against unpredictable data. Python code. Input conversion patterns. This section focuses on safe patterns for converting user input into useful data. It shows how to first read input as plain text, then separately convert it into numeric values or lists. You learn to use a loop that keeps asking for input until it is valid, so errors do not crash the program. Finally, it emphasizes displaying the cleaned and correctly converted results once the input has been successfully processed. The code starts by importing several type definitions from the typing module, such as list, optional, and tuple. These are used as type hints to indicate what kinds of data functions expect as inputs and what they return. Using type hints makes the code easier to read and understand, and it can also help catch errors during development. This function repeatedly asks the user for input until it receives a valid positive number. It trims extra spaces from the user's response, then tries to convert it to a floating point value. If the conversion fails, it tells the user the input must be numeric and asks again. If the number is not greater than 0, it tells the user to enter a positive value and repeats the prompt. Once a valid positive floating point number is entered, the function returns that value and stops looping. This function repeatedly asks the user for input until it receives a clear yes or no answer. It reads the response as text, removes extra spaces, and converts it to lowercase, so capitalization does not matter. If the cleaned input is yes or the letter Y, it returns a positive result. If it is no or the letter N, it returns a negative result. For any other input, it tells the user to answer with yes or no and asks again. This function takes a comma-separated text string, splits it into individual pieces, and cleans each one. For every piece, it removes extra spaces and converts the text to uppercase. Any items that end up empty after cleaning are ignored. The function then returns a list containing only the non-empty, cleaned uppercase items. The code starts by showing a brief message that introduces a simple example of converting user input. It tells the user they will be entering their weight and possibly their favorite exercises. This introduction explains the purpose of the upcoming prompts and makes the interaction clearer and more user-friendly. This code asks the user to enter their weight in pounds and uses a helper function to safely process the input. The function converts the response into a positive decimal number and will keep asking again if the input is invalid. By repeating this process until a valid positive value is entered, the program ensures it always receives a meaningful weight. We ask the user a yes or no question about whether they track their favorite exercises. Their answer is read in, converted to lowercase, and checked to see if it matches yes or no. If the input is valid, the function returns a Boolean value using true for yes and false for no. This gives the rest of the program a clear and consistent response to work with. We begin by creating an empty text field to store exercise information. Then we check whether the user has indicated that they track exercises. If they do, we ask them to type their exercises as a list separated by commas. Whatever they enter is saved in that text field so it can be processed later. This code creates a list of exercises that is always valid. It checks whether there are any exercises, and if so, it sends the raw exercise text to a parsing function that turns it into a cleaned list of exercise names. If there are no exercises, it simply uses an empty list instead. As a result, the exercise list is always either a properly processed list of exercises or an empty list, depending on the user's input. A program prints a brief summary of what the user entered. It uses formatted text to show the weight in pounds, rounded to 1 decimal place. It also reports how many exercises the user provided. This creates a clear and concise overview of the collected data. This script demonstrates safe input conversion by asking the user for their weight and, optionally, their favorite exercises. It requires the weight to be entered as a positive number and keeps prompting until the user provides a valid value. If the user tracks exercises, it then asks for a comma-separated list and converts it into a cleaned list of uppercase exercise names. Throughout, it uses loops and feedback messages to handle incorrect entries and only accepts valid input. In the end, it reports the entered weight and how many exercises were listed, illustrating effective input validation and conversion techniques. Testable I/O patterns. I/O abstraction basics. To make input and output easy to test, treat them as a separate layer between your core program and the console. Your main logic should not deal with the console directly. Instead, input and output functions handle all communication with the outside world. This separation lets your core logic focus only on processing data, while the input and output layer manages where that data comes from and where it goes. As a result, you can change how your program interacts with different environments without modifying the core logic. Abstraction in software is important for handling how programs change over time. During development, you might feed in scripted data for debugging, while in production, the same code should work with real user or network input. In education, Instructors can use fixed inputs and captured outputs to automate grading. And in business, a financial routine might send results to a console for analysts or to a log during batch processing. By using abstract interfaces for input and output, you can swap these different implementations without changing the core program logic, which makes maintenance and adaptation much easier. I/O abstraction in testing means routing all input and output through specific functions so they can be easily controlled and replaced. Instead of relying on unpredictable user actions or external systems, tests use predefined inputs and capture outputs in memory. This creates a single adjustment point that makes tests more reliable, repeatable, and efficient, just as simulators provide a safe, consistent environment in other fields. I/O abstraction plays a key role in creating controlled testing environments in software. Python code, I/O abstraction basics. This material explains how to use simple input and output abstraction so that different input and output handlers can be swapped without changing the main program logic. The core logic should depend only on abstract reader and writer interfaces, not on specific console or test implementations. By designing the code around these interfaces, you can easily switch between console input and output and test input and output. This makes the system more flexible, easier to test, and simpler to maintain. The code starts by importing 3 tools from the typing module: protocol, list, and callable. Protocol is used to define interfaces that other classes can follow, which supports flexible and interchangeable components. List provides a generic way to describe lists of items, and callable is used to specify types that represent functions or methods. Together, these imports lay the groundwork for defining abstract interfaces and managing collections of data in a structured way. This part of the code defines a protocol called reader, which acts as a template for other classes. A protocol in Python specifies what methods a class must provide, without giving their actual code. In this case, any class that follows the reader protocol must implement a method named readLine that returns a string representing one line of input. Using a protocol here creates a flexible interface for reading input, so different reader implementations can be swapped in without changing the main logic that depends on them. This part of the code defines a writer protocol, which is a kind of template that specifies what methods a class must provide without giving their actual implementation. In this case, any class that follows the writer protocol must implement a method called writeLine. That method takes one string argument called text and does not return anything. The purpose of this protocol is to guarantee that any class used as a writer in the program can handle sending output somewhere by implementing this required method. The console reader class is designed to handle input from the console, and it includes a method called readLine. This method displays a prompt asking the user to enter a value in inches, then waits for the user to type a response. After the user enters a line of text, the method returns that input as a string. This allows the program to receive interactive, real-time data from the user through the console. The console writer class is responsible for handling output. It provides a method called writeLine that accepts a piece of text and uses the standard print function to show that text on the console. By centralizing output in this class, It acts as an output handler that can be easily replaced with other output mechanisms if needed, without changing the rest of the program. This class, called ListReader, simulates reading input from a fixed list of strings. When it is created, it receives a list of strings that represents the input data to be processed. It also sets an index to 0 to track the current position in that list. Using this index, the list reader can move through the list one item at a time, mimicking the behavior of reading lines of input in sequence. This method reads items one by one from a predefined list to simulate user input. It takes the current item based on the current index, then moves the index forward to the next position. After updating the index, it returns the item it just retrieved. This creates a simple, controlled way to provide sequential input from a fixed list. The ListWriter class is used to capture output lines in a list instead of printing them. When it is created, it initializes an empty list called lines that will store each line of text it receives. This makes it easy to review and inspect all output later. Such a design is especially useful in testing, where you want to check what would have been printed without actually showing it on the console. This method belongs to a class that manages writing operations and takes a piece of text as input. Its job is to add that text to a list that stores all output lines. By appending each new entry to this list, the method keeps a complete, ordered record of everything that has been written. This stored sequence of lines can then be used for purposes such as testing or logging. This description explains a function that converts a length given in inches into feet and inches. It takes an integer number of inches, then finds how many whole feet fit into that length by dividing by 12. It then uses the remainder from that division as the leftover inches. Finally, it returns a short text that reports the original inches of their equivalent in feet and inches. This function reads a line of input as a string, converts it to an integer representing a number of inches, and then calls another function to turn that value into a description in feet and inches. It then uses a writer to output this descriptive message. By relying on abstract reader and writer components, the function keeps its core logic separate from specific input and output methods, making those easy to change without modifying the main code. The demo console mode function sets up a simple example that uses the console for both input and output. It creates a console reader to handle user input and a console writer to display messages. The writer first prints a message indicating that the console mode example is starting. Then the function calls the conversion routine, passing in the reader and writer so the conversion can read from the console and show the results there. In the function demo test mode, we simulate a user entering 30 inches by creating a reader that supplies the value 30 and a writer that records the output. We then call the conversion function with this test reader and writer so it can read the input, convert the inches to feet and inches, and store the result. After the conversion finishes, we print a message indicating that the output has been captured. Finally, we go through each stored line in the test writer and print it to display the captured conversion result. In the function demo test mode, the program demonstrates how input and output are handled in a test environment. It creates a reader that supplies a single value of 30 inches, simulating user input, and a writer that collects output instead of printing it directly. The conversion routine then reads the input, turns it into an integer, computes the equivalent number of feet and inches, and sends the result to the writer. Finally, the stored output is printed to the console to show how the conversion result can be captured and inspected during testing. This script illustrates input-output abstraction by using interchangeable reader and writer interfaces, so the same conversion logic works in different environments. It has a console mode that asks the user for a value in inches, converts it to feet and inches, and then displays the result. It also has a test mode that replaces real input with a predefined list and captures the output in another list. In test mode, it demonstrates converting 30 inches into feet and inches, showing that the behavior is identical even though the input and output sources are different. This design makes it easy to switch between real and test setups without changing the core conversion logic. Redirecting output streams. Redirecting output streams lets you send text that would normally appear on the screen to other places, such as files or buffers, which is especially useful for testing. Instead of assuming output always goes to the console, you can change the destination so the same code either shows messages to the user or records them quietly during tests. This flexibility makes your programs easier to test and adapt, because you can swap output targets without changing the core logic. Instead of writing directly to the console, programs often send their output to a target that is passed in, such as a file-like object, a logging system, or a testing buffer. For example, a function that reports progress can accept an output destination as a parameter, so it can write to the console in normal use, but to an in-memory buffer during automated tests. This design separates the content of the messages from where they are sent, which makes the code easier to test and adapt to different environments, including web interfaces or remote logging services. Redirecting output streams is useful not only for testing, but for flexibly controlling how a program behaves without changing its core logic. A system administrator can send script output to log files for later review, and a data scientist can save exploratory results for reproducibility. In education, instructors can route student program output into grading tools for automatic comparison. Overall, this approach treats output as a configurable resource, letting you direct messages to the console, a log, or a testing system as needed. Python code. Redirecting output streams. This lesson shows how to redirect output streams using a simple greeting function. Instead of sending the greeting text to the console, you will see how to route that printed text into an in-memory buffer. By comparing the usual console output with the captured output stored in memory, you can clearly see the effect of redirecting the output stream. We import the string IO class from the IO module to create an in-memory text stream that behaves like a file. Instead of sending printed output to the console, we can direct it into this buffer. This makes it easier to capture, inspect, or modify output programmatically. It is especially useful in testing, where you often need to verify what a program prints without displaying it on the screen. The greetUser function takes a name and an output destination, builds a greeting message using that name, and then sends the message to the chosen destination. It uses a print operation that is directed to the specified output stream. By changing this output stream, the same greeting can be sent to different places, such as the console or an in-memory buffer, depending on what the program needs. We store the name Alex in a variable called realName so we can use it later to personalize a greeting. Putting the name in a variable makes the code easier to update because we can change the name in one place instead of editing the whole program. This approach makes the code more flexible and reusable. The script begins by printing a message to the console to show the greeting in the normal way, using standard output. This initial step establishes a baseline for how output usually appears. It prepares the listener to later compare this regular console output with what happens when the script redirects the output elsewhere. The greetUser function is called with a realName value of Alex and an output stream argument. The output stream can be either nothing or the standard output stream from the system module. In practice, this means the function defaults to using the standard output, so the greeting is printed to the console. This setup shows that the function can send its message to different output destinations, but here it uses the default console output. The code changes the destination of the greeting message, so it is sent to an in-memory buffer instead of the console. This means the output is captured rather than immediately displayed. By doing this, the text can be examined or modified later before it is shown or used elsewhere. String I/O is a class from the I/O module that creates an in-memory file-like object, allowing you to capture and work with text output in code. Instead of sending text directly to the console, you can redirect print statements into this buffer. This makes it easy to store, inspect, or modify the output programmatically. It is especially useful for testing or when you need to process the generated text before showing it to the user or saving it. We call the greeting function with the user's real name and send its output to a memory buffer instead of directly to the console. This means the greeting text is stored in memory rather than immediately displayed. By capturing the output this way, we can later inspect, modify, or use it in other parts of the program. This approach is especially helpful for tasks like automated testing or logging. The code first reads all the text currently stored in the buffer. It then removes any extra spaces at the beginning and end of this text. The cleaned result is saved as the captured text. This makes the stored text ready for later processing or display. This line explains that the greeting text, which was previously redirected into an in-memory buffer instead of being printed directly, is now about to be shown. It signals that the program is switching from normal console output to displaying the captured output. This helps clarify the result of redirecting the output stream and makes the difference between regular and captured output clear to the reader. Finally, the program prints the greeting text that was captured in the buffer, adding the word captured in brackets to show that this output was redirected and stored in memory instead of being printed directly. This makes it clear that the text came from a redirected output stream. Overall, this step confirms that the output stream was successfully redirected, stored, and then retrieved for display. This script shows how to redirect output streams in Python. It first prints a greeting directly to the console using the standard output. Then, it uses an in-memory buffer created with the string I/O class from the input and output module to capture the same greeting instead of sending it to the console. After capturing, it reads the text back from the buffer and prints it to the console with a short label in front. This demonstrates how redirecting printed output to different streams can be useful for tasks like testing or logging. Simulating user input. When simulating user input, it is important to separate the idea of receiving data from the physical act of typing on a keyboard. Traditional programs often wait for real-time input, which makes automated testing difficult. To improve testability, your logic should depend on a generic input source rather than direct user interaction. In practice, this means your code should request the next input from an input provider, which might be a real keyboard or a simulated source during tests. By designing functions to accept such providers through a clear interface, you can plug in simulated inputs without changing the core program logic. Simulating user input is a powerful way to test your program across many scenarios, including edge cases that are hard to reproduce by hand. In tools like command line surveys or budgeting assistance, you can script sequences of inputs to cover all possible responses, such as invalid entries or unexpected actions. This makes the program behave as if it's interacting with a real user while actually following a controlled script. As a result, you can verify that it handles errors correctly and produces accurate results without needing a person to type every response. Simulating user input is useful not just to see if a program works, but to evaluate its usability and stability under stress. In applications like quiz tools or help desk systems, you can simulate long sessions, rapid responses, frequent corrections, or odd behaviors such as repeatedly pressing enter with no input to check whether the program remains consistent. Because the software treats simulated and real input the same way, these techniques are valuable for testing, debugging, demonstrations, and tutorials. This flexibility strengthens both the reliability of your software and the way you present it. Python code simulating user input. We will show how to separate the source of input from the program's logic by using simple functions. This lets us plug in either real interactive input from a user or a simulated scripted input provider without changing the core behavior. By passing different input providers as parameters, we can easily test how the program behaves under various input scenarios. This approach makes the code more flexible, reusable, and straightforward to test. The code starts by importing several type hints from the typing module, including callable, list, and iterable. Callable indicates that a parameter should be something you can call, such as a function or an object with a call method. List and iterable specify that certain values are expected to be lists or other iterable collections. Using these type hints makes function signatures clearer, improves type safety, and helps keep the code easier to understand and maintain. The ask-for-name function takes another function as its input, which is used to collect user input based on a prompt. It creates a prompt asking for the user's first name, then calls the provided input function with that prompt. The response is trimmed to remove extra spaces, and if the result is empty, the function returns the default name, guessed. This design makes it easy to swap between real user input and simulated input while keeping the same logic for handling the name. The greetUser function takes another function as an argument, which is responsible for handling input prompts. It passes this input handler to a helper function that asks for the user's name and returns it. After getting the name, Greet User prints a welcome message that includes the user's name. This design makes it easy to switch between real user input and simulated input for testing. The Real Input Provider function takes a single string argument that serves as prompt text for the user. It displays this prompt and waits for the user to type a response. Internally, it relies on the standard input mechanism to capture whatever the user enters. This makes it a flexible way to gather real-time user input whenever interaction is needed. The Scripted Input Provider class is used to simulate user input by returning a fixed sequence of predefined answers. Its constructor receives an iterable of strings representing these answers, converts them into a list, and stores them internally. It also keeps a current index starting at 0 to track which answer should be returned next. Each time the provider is used, it returns the next stored answer in order, creating a controlled and repeatable simulation of user responses. This method is called when the object is used like a function, and it receives a prompt as input. It first checks whether the current position has passed the end of the scripted answers list. If so, it announces that no more answers are available and returns an empty string. If there is still an answer available, it selects the answer at the current position, reports the prompt, and the chosen answer. Then advances the position, so the next call will use the following answer. Finally, it returns the selected answer. The Run Demo function first announces that it is starting a simulated input demonstration using scripted answers. It creates a scripted input provider with a list of names such as Alice and Bob, and uses this provider when calling the Greet User function, so the interaction is driven by predefined responses. It then announces that it is starting an interactive demonstration with real keyboard input. This time, it calls the Greet User function using the normal input provider, so it can capture actual user input from the keyboard. The Run Demo function first announces that it is starting a simulated input demonstration using scripted answers. It then creates a scripted input provider with the names Alice and Bob and passes it to the Greet User function, which pretends these are real user inputs. After the simulated run finishes, it prints a message to indicate that it is switching to an interactive demo using real keyboard input. Finally, it calls the Greet User function again, this time using a real input provider that reads actual user input from the keyboard. This Python script shows how to separate input handling from the main program by using a flexible input provider. It first uses a scripted provider that supplies predefined names, such as Alice and Bob, to simulate user interaction and print greetings. It then switches to real interactive input, asking the user to type their name on the keyboard. By allowing the input method to be swapped without changing the core logic, the script becomes easier to test and adapt to different input sources. In this lecture, you learn to use print with custom separators, end characters, and file targets to control console output formatting. Use input to read user input safely and convert it to appropriate types using other built-ins. And structure code so that print and input usage can be redirected or mocked for testing. In the next lecture, Lecture B, we will go over open and globals. Thank you for your attention. See you all in the next lecture.